So at this point, we will be discussing about refraction. Clinical refraction is selecting a lens of such power that when placed before the eye, its secondary focal plane will coincide with the four-point plane of the eye. So our goal here is a comfortable and satisfied patient with best corrected vision, binocular vision with accommodation relaxed. Basically, refraction is determination of the error of refraction or the refractive status of the eye. And that is the amount of the prescription glasses that you will prescribe in your patient. So there are two types of refraction, the objective refraction and the subjective refraction. Objective refraction is also known as a manifest refraction, and it is being done with the use of retinoscope or autorefractometer. And subjective refraction is dependent on patient's response. With this, you determine by subjective means the combination of spherical and cylindrical lenses necessary to provide the best vision, again with relaxed accommodation. We also have what we call cyclorefraction or cycloplegic refraction or wet refraction. This one is being done with the use of cyclodrugs, cycloplegic drugs. For example, atropine, cyclopentolate, and tropicamide. Yeah, you can do cyclorefraction both subjective and objective refraction. Here are the instruments that we use when doing refraction. On your left are the retinoscope and the autorefractometer, while on the right is your poroptor and your trial lens set. The reti and autoref is for objective refraction, while the poroptor and trial lens set is for subjective refraction. Here are the steps in refraction. Number one, get the best visual acuity, get the vision first. And then after that, you determine error of refraction, whether patient has myopia, hyperopia, or astigmatism. And then get the pupillary distance. Getting the PD is very important because you base or you set your poropter um, optical centers depends on the amount of your pupillary distance or the value of your pupillary distance. Then you do objective refraction, then subjective refraction, and then if the patient is presbyopic or with age more than 40 years old that needs bifocal correction, then you get the reading aids. And the final step is your prescription writing. Okay, in visual acuity determination, don't forget to use pinhole. Once you ask the patient to read and determine the level of visual acuity, you use pinhole for you to identify whether the cause of blurring of vision is secondary to EOR, because with pinhole it will improve, or the blurring of vision is pathologic. With pathologic condition, VA will not improve with the use of pinhole. So here's how to get your pupillary distance. Just look at the center of the right pupil and the center of the left pupil. Measure the distance. So like in this case, you have a 62 millimeter distance. So that is your pupillary distance. And then set either your poroptor or your trial lenses at 62 millimeter optical centers. So the PD should be parallel with your optical centers. Also, when you prescribe the eyeglasses, you need to write the patient's PD, like in this case, 62 millimeter. In getting the distance PD, you just have to ask the patient to look at the distance and then measure the centers of right and left pupils. And for near PD, you just have to ask a patient to look at a closer distance or at an object in front of the patient and then measure the centers of the pupillary distance. So with that, you get the distance PD and the near PD. So the considerations in refractions are determination of the spherical power, whether it's plus or minus. You also determine the cylinder axis, Use determine the cylinder power, and of course your reading adds for presbyopics. So let's start with objective refraction. Objective refraction is being done or performed with the use of retinoscope. So here are the parts of the retinoscope. Okay, so this is a Welch-Allen type retinoscope. So you have there the green button, that is the control of light. Okay, rotating it will open the power of the retinoscope. You have the forehead, the peephole, okay, the cross-linear polarization filter, and the focusing sleeve. The sleeve can be manipulated upward and downwards, or you can rotate it to rotate the streak. When you bring down the sleeve, it will give you a plano effect, and then moving it upward will give you a concave mirror effect. In the second picture on your right, this is how you do your retinoscopy. Okay, the patient is about an arm's length away from you. Okay, so retinoscopy is an objective technique for determining the refractive power of the eye. So you look for the sphere, the cylinder, power, and the axis of the cylinder. It has components, the illumination system, and the observation system. Okay, so it is an objective measurement of astigmatism and spherical component. You also, with retinoscopy, you'll also be able to determine some media opacities or optical defects. And there are two types, the Copeland and the Welch-Allen. And we commonly use the Welch-Allen. Okay. So again, the components are light bulb filaments, which is linear. Okay, we have the mirror, the sleeve. Actually, it adjusts separation of filament from mirror. So in the standard clinical practice, the sleeve is always in a downward position to have a plano mirror setting. Okay, the optical principle of retinoscopy is locating the far point of the eye. So far point is the point in distance where I can see when accommodation is relaxed. So in cases of emmetropia, the far point is located at the infinity. While in cases of myopia, the far point is in front of the eye, as you can see in the middle illustration on the right. And in hyperopia, we have a virtual far point that is behind the eye. Focal point is different from far point. Focal point is where object from optical infinity focuses inside the eye. So in cases of emmetropia, when you're talking about focal point, the focal point of emmetropia is exactly on the retina. Okay, while in myopia, the focal point is in front of the retina, and in hyperopia, the focal point is located behind the retina. Okay, so in performing retinoscopy, our main goal is the neutrality reflex, or a neutral reflex. When you say neutral or point of neutrality, light reflex fills the pupil of the patient. So in this case, the far point of the eye conjugate with peephole. Okay, so in retinoscopy, our concern is the movement inside the pupillary area. So you call it retinoscopy reflex. So like in this video, the outside light is the streak of your retinoscope. So positioned vertically. All right, you move your retinoscope right to left, okay, in the horizontal motion, and then observe the reflex inside the pupillary area. We call it reti reflex or retinoscopy reflex. If your retinoscopy reflex moves with the movement, or it goes with the movement of your streak, meaning to say when you sweep or you move your streak, right to left, or you move it to the right and then the reflex moves to the right, that is with motion retinoscopy reflex. Okay. So if the reflex is moving away from the movement of your streak, meaning to say, when you move your streak to the right, then the reflex goes to the left, okay? That is an against motion retinoscopy reflex. And if there is no observable movement, we call it a neutral retinoscopy reflex. So this is the point of neutrality. So when doing retinoscopy, what we want to achieve is the neutrality position, or the neutral point, or neutral reflex. So what is against and with movement? When you see an against movement, meaning to say, the error of refraction is always myopia greater than working distance. Okay? We will discuss more on the working distance as we go on. So against movement is only seen in myopia greater than working distance. At this point, the far point is between peephole and the patient. And when you see a with movement, there are three conditions in with movement: emetropia, hyperopia, and myopia less than working distance. So if you have with movement, the far point is beyond peephole or behind the examiner. Okay, so another important thing is the working distance. So when you're doing retinoscopy, you are arm's length away from your patient. So you measure that distance. On the average, that is about 67 centimeter, or the dioptric equivalent of that is 1.5 diopter. So for shorter arm's length, sometimes it is more than or less than 67 centimeter. So you can use a 2 diopter equivalent arm's length. Okay. So in cases of hyperopia, you will observe a with movement. So in this case, if you have a with movement, you just use a plus lens to achieve neutrality. And if you see an against movement in cases of myopia, you just use a minus lens to achieve neutrality. And then if you have already neutralized the reflex with a certain power, you subtract your working distance. The amount of lens that neutralizes your movement is what we call the gross retinoscopic findings. And by subtracting the power of your working distance, will give you the net retinoscopic findings. So for example, you were able to neutralize the the reflex with plus 3 diopter, and then you have a working distance of minus 1.5, your gross retinoscopic findings is plus 1.5. So in this video, you will observe a with motion. So as I said, if you have a with motion, you need a plus lens to neutralize the motion. Okay? So again, with motion, you need a plus lens to achieve neutrality. Like in this case, with plus 2 still with, but with plus 3, you have a neutrality or a neutral reflex. You achieve neutrality. Okay, so your gross retinoscopy is plus 3 diopter sphere. That is the amount of lens that neutralizes the movement. Okay, so you subtract your working distance, which is always 1.5 minus, so algebraic addition, the net retinoscopy now is plus 1.5 diopter sphere. Okay, so in the second video, you will observe an against movement. So if it's against, you need to neutralize with minus lens. But in this case, minus 4 turned the against into a with motion. So I think you overcorrected the eye. So again, back with minus 3 and it's neutral. Okay, so against motion, to achieve neutrality, you need to place a minus lens. So in this case, your gross retinoscopy is minus 3 diopter sphere. You subtract your working distance of minus 1.5 diopter sphere. You will now have your net retinoscopy of minus 4.50 diopter sphere. Again, you add algebraically. Okay, so there are some clues in the observation system. First, the movement. If it's with, okay, you add plus lenses. If it's against, you add minus, you place minus lenses. You also check for the speed because in a high grade EOR, the speed of the reflex is slow, while if it's fast, it will give you an idea that the grade is low. And in terms of brilliance, it is dull if the grade is high, and you will observe a bright reflex if the EOR or the grade is low, and narrow width if it's high grade, and broad if it's low grade. So that is those are the clues in the observation system. All right, let's begin retinoscopy step by step. Number one, determine your working distance. Number two, determine type of error of refraction. Number three, determine axis of principal meridians. Number four, you neutralize meridian 1 first. Number 5, you neutralize meridian 2. Number 6, you determine the spherical power, then the cylinder axis, and lastly, the cylinder power. Okay, so how do you get the working distance again? So measure your arm's length because uh, the distance between you and the patient is the length of your arm. So in this case, the arm's length is 6 to 7 centimeter. So by using the formula to convert it to dioptric power, D is equal to 1 over F, you will have 1 over 6 to 7 centimeter. So uh, that will give you a 0.0149 multiplied by 100 because it should be in meter. Now that will give you a 1.49 round up to 1.5 diopter. So that is the value or the dioptric power of your working distance. Again, on the average, working distance is almost always at 1.5 diopter. So if you are shorter, you compute for the exact amount of your working distance or shorter arm's length. Okay. Next is determine the type of error of refraction. Okay. So approaching the far point from with side is better than from the against side. Meaning to say, when you start doing retinoscopy and observing the reflex, you start with working in a with side. So in the video, upper video on your right, you have a with motion, and you will only see with motion in cases of hyperopia, emetropia, or low myopia. While in the lower video, you will see an against motion only in one case, and that is myopia greater than working distance. So if your working distance is 1.5, myopia more than 1.5 will always give you an against motion. Okay? And then the third one is determine the axis of principal meridians. So principal meridians could be in the vertical horizontal, but sometimes it is in the oblique position, like in this case. So if the appearance of your reflex is like this, you should rotate the streak in order for you to position the streak and the reflex parallel to each other. So the intercept and reflex should be positioned parallel. So that is what we call break. So you just have to rotate the streak until you align the reflex and your streak. Okay, so fourth step, neutralize meridian 1. Okay, so the streak actually tests the power of the corneal meridian that it sweeps across. So if your streak is positioned vertically, you are sweeping it horizontally, meaning moving your streak right to left. What you are actually scanning is the horizontal meridian. Okay, so that's your streak vertically positioned, moving it side by side, right to left. You're actually scanning the horizontal meridian, which is at 180 degrees. Okay, so theoretically, it is better to neutralize first the higher plus or the lower minus meridian. So in practice, it is more practical to have a routine which is start your neutralization with the slit at vertical meridian first. So that is at the 90th. Okay. And then next is rotate the streak 90 degrees away from first meridian for you to determine or to scan the power of the second meridian. All right, so you rotate it 90 degrees away. So if first meridian is at 90th, the second meridian will be at 180th meridian. That is 90 degrees away. In cases of oblique positions, oblique meridians, if your meridian 1 is at 45 degrees, 90 degrees away is 135 degrees. Okay, that is your meridian 2. Always remember, meridian 1 or meridian 2 is 90 degrees away from your meridian 1. Okay. So next is determination of spherical power. How will you determine the amount or the spherical component after achieving neutrality? So always go for higher plus power, all right, and then subtract your working distance. So in this case, in this example, first example is plus 4. Your working distance is minus 2. So add algebraically, your spherical component is plus 2. Next is determine the cylinder axis. The power of a cylinder is actually perpendicular to its axis. It's 90 degrees away. The streak tests the power of the meridian perpendicular to the streak axis. So for example, your retinoscopic streak is positioned at the vertical meridian or at 90 degrees. Your movement of the streak is sweeping it right to left or horizontally. So in doing so, you are actually scanning the power of the 180th meridian. Okay, so use the flat meridian as your axis. That is the highest plus and the weakest minus. So in the example below, you have plus 4 axis 180 and plus 2 axis 90. When you write it in a spherocylindrical component or formula, you will write it as plus 4 diopter sphere combined with minus 2 diopter cylinder, and your axis will be the axis of the higher plus. All right, so in the example below, you have minus 2 axis 90 and you have minus 4 axis 180. The spherocylinder formula will be minus 2 diopter sphere combined with minus 2 diopter cylinder, and the axis will be the highest plus, which is 180th. All right, so let's make it a lot clearer by writing the powers into the power cross. So you have here plus 4 at axis 180 and plus 2 axis 90. You write plus 4 since the axis is 180th, that is the flat meridian. The power is located vertically or at 90. So meaning, when you say plus 4 axis 180, the plus 4 is located 90 degrees away from 180, which is 90 degrees, right? And with plus 2 axis 90, when it says axis 90, the plus 2 power is located at the 180th, 90 degrees away from your 90th meridian. So your plus 2, you will write plus 2 in the horizontal line of your power cross. So to get the spherical component, get the higher plus first, which is the plus 4. And then the cylinder power is the difference between the two powers, which is 2 diopters. And to get that, you just subtract algebraically. When you do that, you change the sign of the subtrahend. That will now become minus. That's why it becomes minus 2. So the spiral cylinder formula is plus 4 diopter sphere combined with minus 2 diopter cylinder. And your axis is the area of the highest plus. And that is the vertical. So the axis is 90 degrees. All right. So in the second example, you have a minus 2 axis 90. When it says axis 90, the minus 2 is located not in the 90, but at 180th meridian. So in the power cross, you write minus 2 over the horizontal line. And the second one is minus 4 axis 180. If it says axis 180, that is the flat meridian or no power. So if it says axis 180, the power of the minus 4 is actually at the vertical meridian. So you will write it in the vertical line of the power cross. So minus 4 is at the vertical line. Okay, so let's get the sphere. So the spherical power, again, is the highest plus in this case. So it's minus 2. So the cylindrical power is the difference between the two numbers, the two powers. So that's 2 diopters. And it's minus, subtract algebraically. Okay, so the axis now will be the area of the highest plus. So if you look at the cross, the power cross, the highest plus is located vertically. Okay? Oh, I'm sorry. The highest plus is located horizontally. So the axis now is 180. So it's minus 2 diopter sphere combined with minus 2 diopter cylinder at axis 180. Okay. How about the power? The difference between higher plus meridian and the lower plus meridian is your power. So plus 4 and plus 2, the difference is 2 diopter. Plus 2 and plus 4, the difference is 2 diopter. And it always goes with a minus sign. The cylinder is always in a minus sign. You only see a plus cylinder sign in other countries, especially like US. Okay, but here we use a minus cylinder form. Okay, so never forget to subtract the working distance in your final refraction. And your end point is always the net retinoscopy. So again, if you have a gross, you just subtract the working distance, and then that will be your net retinoscopy. There are 3 important steps that you always have to remember. First, always start with motion. Okay, so check the 2 principal meridians first, and then look for a with motion. Okay, and then you start from there. So if the 2 principal meridians have different characteristic of streaks, you just choose the one with brighter and thinner streak. So which means you are nearer to neutrality. That neutralize that first as your primary meridian. Add power to neutralize the reflex. So plus for with motion, minus power or minus lenses for against motion. And never forget to subtract the working distance to arrive at net retinoscopy. Okay, so let's have some video illustration here. So here your streak is vertically positioned. So that's one of the meridian. Okay, that's a a primary meridian. It's a with motion. You neutralize it, being with, neutralize it with plus, increase plus lenses. And as you go to near the neutrality, you will observe that the streak is getting thinner and brighter. Okay, with plus 2, and then increase the plus until you reach the point of neutrality. All right. So the neutralizing lens here is plus 250 for with motion. Check the secondary meridian. If it is also neutral, then meaning to say you have a pure spherical component. So your gross retinoscopy is plus 2 diopter sphere. You subtract your working distance of minus 150 diopter sphere, then you will get a net retinoscopy of plus 1 diopter sphere. The second video will show you an against motion. So being against, what you need to neutralize it is a minus lens. Okay. So always remember, neutralize against motion with minus lens. So here you have an increasing minus powers. So you have minus 50 minus 75 minus 1. And it's neutral with minus 1 to 5. Okay, so check the other meridian, the secondary meridian. Okay, it's also neutral. So you have a pure spherical component, a minus uh, neutralizing lens. So your gross retinoscopy is minus 125 diopter sphere. Now you have a working distance of minus 150. You will have a net retinoscopy of minus 2.75 diopter sphere. Okay, those two videos were actually pure spherical. However, it will be different if you have an astigmatic component and you call it a spherocylinder combination. So there are two techniques in neutralizing spherocylinder component or with astigmatic component. The first one is you can use two spherical lenses. That is what we call sphere to sphere technique. So use spherical lenses to neutralize both the primary and secondary meridians. While the second one is a sphere to cylinder technique. So in this technique, you utilize a spherical lens for the primary meridian, or yes, and then a cylindrical lens to neutralize the secondary meridian. So a combination of a sphere and a cylinder lenses to neutralize the um, spherocylindrical component. So let me show you a video illustration of a sphere-to-sphere technique. So here, as you can see, the primary meridian is vertical and the secondary meridian is located horizontally. Okay. So you neutralize the primary meridian first, being a with movement, neutralize it with plus spherical lens, an increasing spherical lens, okay, plus 75, you increase with plus 1, it's already neutral. So you write the plus 1 at the horizontal line of the power cross, and then proceed with your secondary meridian. It's also a with motion, so we will be using another spherical lens here. Since it's a with motion, we are neutralizing with an increasing plus lenses, okay? With plus 150, it's already neutral. So you put your plus 150 over the vertical line of your power cross, and then check again both meridians, the two principal meridians. Okay, both were neutralized already. All right. So in this case, your spherical component again is the highest plus. So that's plus 150. Okay. Your cylindrical component is the difference between the two numbers, okay? Between plus 1 and plus 150. So the difference is 50 diopters. Okay, and your axis is, look at the power cross, okay? The one with the higher plus will be your axis. That is the flatter meridian. So that is axis 90. So the combination now for your gross is plus 150 diopter sphere combined with minus 50 diopter cylinder at axis 90. Then my working distance here is minus 1.50 diopters, 1.50 diopters. So my net retinoscopy now is plano combined with minus 50 diopter cylinder at axis 90. Okay, so that's a sphere, that's the sphere to sphere technique. Neutralizing two meridians, utilizing both spherical lenses. While in the second video, I will be showing to you the sphere to cylinder technique, or the, yeah. So, all right, in the sphere to cylinder, first determine the two principal meridians. Okay, so here we have the primary meridian as with motion. You neutralize it first with the spherical lens. Plus 1, plus 150. Okay, getting nearer to neutrality with plus 2, 250. All right, so increase the plus until you reach the neutral point. Now, this meridian was neutralized with plus 3 diopter sphere or spherical lenses. But as you observe, the secondary meridian has an against motion. So being against, you neutralize it with minus cylinder lens. And always look at the marker of your cylinder lens. Make sure that it is parallel to the streak. Okay. So increase your cylinder power. Against motion, increase the cylinder. Okay. 150, 175. Now it's neutral with minus 2. All right. So check both meridians. Vertical, neutral, horizontal, neutral. So in this case, we use a plus 3 here to neutralize the first meridian or the primary meridian. And the secondary meridian is an against motion neutralized with minus cylinder. This is a minus cylinder. Take note of the uh, axis, axis line. Okay, it is placed horizontally. Okay, so your spherical is plus 3 diopter sphere. And then here, you don't have to subtract because you already used a minus cylinder to neutralize the secondary meridian. So it's already a minus 2 diopter cylinder. And then axis, look at the look at the position of your streak in your secondary meridian. It is positioned horizontally, and your axis reference here is also horizontally positioned at 180th. So therefore, your axis is 180. So the gross here is plus 3 diopter sphere combined with minus 2 diopter cylinder at axis 180. You subtract your working distance. By the way, in a spherocylindrical uh, component, the working distance is only being subtracted at the spherical component. You do not touch the cylindrical powers. Okay, so plus 3 diopter sphere, you subtract your working distance of minus 150. That is actually add algebraically to be specific. Okay, you will get a plus 150 diopter sphere combined with minus 2 diopter cylinder axis 180. That is your net retinoscopy. So again, in the spiral cylinder technique, you neutralize the first meridian with a spherical lens. and then neutralize the secondary meridian with a cylinder lens. Okay, what if in case of oblique astigmatism? When I say oblique astigmatism, the primary meridians, the principal meridians are not located in the vertical and the horizontal areas. All right, so in oblique, sometimes they are away from the vertical and the horizontal meridian. So like in this case, all right, so your streak is positioned vertically, which what we usually do. However, as we can see, the streak is not aligned with the retinoscopic reflex, meaning to say you have an oblique astigmatism. They are not parallel. So, okay, so what you need to do is you rotate using the sleeve of your retinoscope. You rotate the streak until the reflex and the streak are aligned in a parallel position. Okay, all right, and then once you are able to determine the location of the principal meridians, you can now proceed with your neutralization. So determine primary meridian first. So this is the first meridian because the streak is brighter. Okay, so it is the one that is nearer to neutrality. Since it's an against motion, you neutralize it with minus spherical lens, an increasing minus spherical lens until you reach the point of neutrality. All right, with minus 150, getting nearer. And it's actually neutral with minus 2 diopter sphere. There, okay. So you rotate your streak to get the secondary meridian 90 degrees away. So in the first meridian, it's in the area of 45 degrees. So 90 degrees away is 135 degrees. Okay, so it's an against motion. You neutralize it with a minus cylinder. This is a spiral cylinder technique. So take note of the position of the axis reference of your minus cylinder. All right, so make sure that your axis is located parallel, okay, to your streak and your reflex. All right, so you align it to get the correct axis. All right, so again, you continue neutralizing it. We, against motion, increase the minus cylinder power to reach the neutrality or the neutral point, minus 115. Increase more the minus cylinder power to minus 2 until you reach the point of neutrality. Okay, so both meridians are now neutral. Right, so since this is a spiral cylinder technique, okay, minus 2 is your sphere, minus 2 is also is your cylinder at axis 135. So here, your gross retinoscopy is minus 2 diopter sphere combined with minus 2 diopter cylinder. Your axis, remember, in spiral cylinder technique, uh, your endpoint here, look at your endpoint, look at the position of the streak, and that will be your axis. So here it's the secondary meridian, the endpoint is at 135 degrees. So the axis is 135. You subtract your working distance to your spherical component. That will now become, again, to be specific, it's add algebraically. So that will now become minus 3 diopter, minus 350 diopter sphere combined with minus 2 diopter cylinder at axis 135. Okay, so we are now done with objective refraction. We will now proceed with subjective refraction. As the term implies, subjective refraction is dependent on patient's response. All right? You are presenting lenses in front of the eye and then asking the patient which is clearer or better lens. Okay. So in subjective refraction, you are performing this monocularly. Okay. In contrast with objective refraction, you do it binocularly. So this monocular testing. So at first, you direct the patient to read the smallest print, and then So then from the smallest print, you start applying a plus lens. So plus lens to blur the vision of the patient up to the level of 20 over 200. So again, so for example, the best VA of the patient is 20 over 40. You apply plus lenses, increasing plus lenses to reach the point of blur at a 20-200 level. So that is what we call a fogging technique. So why do we need to do that in subjective refraction? We need to relax the accommodation first. Okay? So from best VA, decrease the visual acuity to the blur point of 20-200. Usually you do that by adding plus lenses. Okay. So sometimes at plus 2, it's already blur at 20-200 level. Your plus 2 is your fogging lens. But if patient is hyperopic, plus 2 might or plus 2 may give a better vision. So you increase more the plus power until you fog the eye to reach a blur of 20 over 200. So that's the biggest letter in your Snellen chart. Okay. Um, then from there, for example, it's already blur. The 2200 is blur at an amount of plus 2. You slowly reduce the amount of sphere in front of the eye in half diopter steps or 2 clicks until the patient see the best line. So for example, plus 2 blur at 2200, you decrease it by plus 150, plus 1, plus 50, plano, then going towards the minus side until the patient reach the best visual acuity with the smallest print. Okay. So for example, VA was uh, or patient achieve a visual acuity of 20/20 with plus 0.50. So the power of the lens is plus 0.50. For example, the patient was able to see the 20/20 level, that is the best line for the patient with an amount of, on the minus side, for example, minus 0.50. Therefore, the power of the lens is minus 0.50. Okay. So importantly is do not continue to reduce plus power or adding more minus. Okay. So because we always want uh, an accommodation relax. Okay. So as you introduce a choice of two lenses for the patient to discriminate, ask the patient which is clearer, one or two. So this is why it was called a subjective refraction. You need the patient's response as you add different amount of lenses. So you just have to ask the patient which lens is clearer or better. Okay. So the goal of subjective refraction is to find the best sphere, meaning the most plus to best acuity. So as you can see, subjective refraction is a lot easier than objective refraction because objective refraction is just putting a succeeding lens, okay, just to reach the best visual acuity. And that will all depends on patient's response. Okay. So for example, you were able to arrive at a spherical component in subjective refraction. Now you need to determine whether this patient has an astigmatic component. So how do you do that? So after placing the subjective refractive power, you now ask the patient to look at the astigmatic dial. Okay. Uh, the one in the photo, okay, that is an astigmatic dial. It is also called as sunburst dial, fan dial. Okay, this is used to determine presence of astigmatism. So with your subjective lens power, you add plus 0.50 diopter sphere on top of it. The purpose is again to relax the accommodation. Okay, and then, so for example, your uh, lens, subjective lens with the best visual acuity is plus 50, then you add an additional plus 50 before asking the patient to look at the astigmatic dial so that the accommodation is relaxed. Okay, then ask the patient if he sees the lines in the astigmatic dial as equally clear or equally blur, or is there a line that appears to be darker than the rest? Like in this example, the darkest or the brightest line is the at 90th or the vertical line. So if the patient reports that the brightest line is at 90th, meaning they are not equally clear or equally bright, so 90 degrees from that, perpendicular to that, is the axis of the cylinder. So first of all, when he sees that the lines are not equally clear, meaning to say there is an astigmatism. And to determine the axis of the astigmatism is perpendicular or 90 degrees away from the brightest line. So if the brightest line, the clearest line is at 90th, the axis of this astigmatism is at 180th or axis 180. Okay. So now start adding minus cylinder. Since this is an astigmatism, we will utilize a minus cylinder lens. So okay. On top of your spherical component from the subjective refraction, initial subjective refraction, you add a minus lens with axis at 180th meridian or axis 180. So you start by giving a minus 0.25, minus 50 by 0.25 increment. And you will ask the patient that they should report or he should report if the lines appears to be equally clear. So once the lines are clear, that is your endpoint. So for example, the lines are clear with giving minus 0.50 diopter cylinder. So you stop from there. So meaning to say your cylinder power or the astigmatism of the patient amounts to minus 0.50. All right, so you remove your accommodative lens of plus 0.50. So in the initial example, we have plus 50 with combination of minus 50 diopter cylinder. Your axis is at 180. So that is now your spherocylindrical component or the astigmatic correction. Okay. So after doing everything, we will now proceed with refinement with Jackson cross cylinder. So you're done with your retinoscopy or with your subjective refraction. So place the best spherical or best refraction in your refracting unit, whether poropter or trial frame, or your net retinoscopic findings, and start performing Jackson cross cylinder. Okay, so what is a Jackson cross cylinder? This is a unique lens actually. This is the only lens with a combination of a plus and a minus cylinder in one lens. Okay, so the one in the Poroctor is a plus 0.25 and a minus 0.25 cylinder. In the trial lenses, it comes into 0.25, 0.50, or sometimes 0.75. And the red dots are the axis of the minus cylinder, and the white dots are the axis of the plus cylinder, both in the trial or in the trial lens set or in the Poroctor. Okay, so in refinement with Jackson cross cylinder, you are checking first. So the refinement meaning you are trying to um, see if your spherical and cylindrical component after your initial refraction are exact and correct. Okay. So in refinement of Jackson cross cylinder, you have to determine the axis first before the power of the cylinder and then the sphere. Okay. So remember, in Jackson cross cylinder, you have to check the correct axis first, followed by the cylindrical power, and then spherical adjustment if needed. So axis first, power next, last is the spherical component. Okay, so in checking the axis or refinement of the axis in the in JCC, we have the term straddling technique or the straddle technique. Straddle means you put your axis, the initial axis that you have from your net retinoscopy, you place it between the minus and the spherical component of your Jackson cross. So, like in the illustration below, if, for example, after net retinoscopy, you have your axis is 90. When you are trying to refine this axis, you perform the straddling technique, align the handle of the cylinder or the handle of the JCC in your initial axis, which is at 90. In doing so, you are actually uh, placing your axis in between the minus side of the JCC and the plus side of the JCC, like in the drawing below. Okay. So the next is checking the cylinder power. So refinement of your cylinder power, how do you do that? If we have a straddling technique in checking the cylinder axis, the term now that we apply in checking the cylinder power is the on axis. Okay. What do you mean by on axis? On axis is aligning uh, the minus power of the Jackson cross to your axis, uh, to the axis power or to the axis meridian. Sorry, so that is on axis. So, for example, your axis is at 90. You position the Jackson cross red marker at 90. At this point, I'll be showing you a video illustration on how to perform your Jackson cross cylinder using your Proptor. So initially, you have to check or make sure that the other eye is occluded because this is done monocularly. Then place in the Proptor your net retinoscopic findings or your best refraction. In this case, you have -1 diopter sphere combined with -75 diopter cylinder at axis 180. And then you ask the patient to look one line above the best line. That is your test target. Okay, so the first step is refinement of your axis. And in doing that, you have to do the straddling technique. The straddling technique is aligning the handle of your cross cylinder parallel to your initial axis. Right, in straddling technique, your axis is actually 45 degrees away from your red marker and 45 degrees away from your white marker. So white marker is the power of the or the plus power of your cross cylinder, and the red marker is the negative power of your cross cylinder. Okay, so the instruction here is you have to tell your patient while looking at one line above the best line, you have to instruct your patient that you will be introducing two lenses. All right, and they have to tell you which lens appears to be better or clearer. You will introduce lens one, then flip your Jackson cross to introduce lens 2, and then ask the patient which lens appears to be clearer, lens 1, lens 2, or the same. All right, so with while your JCC is straddling your axis, you ask the patient which is better, lens 1, red above, or lens 2, red below. Okay, again, lens 1 or lens 2, which is better? or are they the same? If the patient prefers lens 1, that means the red marker is above your axis. So rotate, chase the red part, go to the red, and then rotate it 10 to 15 degrees away. And also position your initial axis to 165. So if your cylinder is less than 2 diopter, you can move your axis or Jackson cross cylinder axis 10 to 15 degrees away. But if the cylinder is high, you move your cylinder axis by about 5 degrees. So repeat the same procedure. Tell the patient which is better, lens 1 or lens 2, or are they the same? Repeat again, lens 1 or lens 2, are they the same? And the patient chooses lens 2, so you move again 15 degrees towards the red dot. And then move also your initial axis. Okay, so at this point, you are now at 150 degrees axis. And then again, with this new axis, ask the patient which is better, lens 1 or lens 2 with red above, or are they the same? Then again, lens 1, lens 2, or are they the same? And if the patient reports that they are now equally clear, your new axis now is 150 degrees. All right, so next thing to check is your cylinder power. So in checking the cylinder power, make sure that your red dot is on axis. On axis means that your red JCC power or negative power is aligned to your new axis. All right, that is on axis. And then again, introduce two lenses by flipping the JCC. As a patient, which is better, lens 1 with white on axis or lens 2 with red on axis. Okay, or are they the same? Repeat again, lens 1 or lens 2. If the patient prefers lens 2, then you need more cylindrical minus power. You increase your cylinder by 0.25 diopter cylinder. And then ask again the patient, which is better, lens 1, lens 2, or are they the same? Repeat again, lens 1, lens 2, or the same. If the patient prefers lens 2, then you need again more minus by 0.25. And at this point, you already have added a 0.50 diopter cylinder. For every 50, you adjust your cylinder power by 0.25 in an opposite direction. And then again, you ask the patient, which is better, 1 or 2? Lens 1 or lens 2, or are they the same? If the patient reports that they are the same, you are now done with the refinement of your cylinder power. All right, so you have to remember that for every 0.50 diopter change in your cylinder power, you also have to move your spherical power by 0.25 in the opposite direction. Meaning, if you are increasing the minus cylinder power, you will decrease the minus spherical power. So in this case, we added 0.50 diopters cylinder. So we decrease 0.25 diopter sphere. So your final prescription now is minus 0.75 diopter sphere combined with minus 125 diopter cylinder at axis 150. There are important notes in refinement with JCC. Number one, place your net refraction over the phoropter or trial frame. Number two, patient's test target is one line above the best line. Number three, refine axis first. Straddle the axis by placing the handle parallel to the initial axis. Number four is move the axis towards the red marker because we are using a minus cylinder form. So you adjust by 10 to 15 degrees for cylinder less than 2 diopter. While more than that, especially for higher cylinder powers, yeah, the movement is only about 5 degrees. Okay, so fifth one is refine the cylinder power next by placing the red marker over the new axis. And last one is for every 0.50 diopter change in cylinder power, Adjust the spherical power in opposite direction by 0.25 diopter. So we are done with subjective refraction, refinement with Jackson cross cylinder. Now, here's another technique to further check if you are in your right spherical and cylindrical power. Okay, if your refraction is really correct. We use the duochrome bichrome test. The duochrome bichrome test is presenting two different filters, red and green filters. Okay, then ask the patient to look at the letters over the red filter and compare it with the letters over the green filter. So you ask the patient, are they equally clear, or one appears to be clearer than the other? So if the patient reports that the letters on the red are clearer, then you are still in the myopic side. You need more minus to make it equal with the green filter. But so you add minus lens. If the patient reports that the letter on the green is clearer, then you are on the hyperopic side. You add plus lens to make it equal with the other with the red filter. That is the duochrome bichrome test. So the principle of that is if you have reached the point, if you are in emetropia, the yellow uh, the yellow color should fall exactly on the retina. So meaning to say the green and the red should have an equal appearance. If red is clearer, letters on the red are clearer, meaning to say the red color is the one placed exactly on the retina. So patient is still myopic, you add minus. So red, add minus. And if green is clearer, the green is the one falling exactly on the retina. So the eye is still hyperopic. You put plus lenses to move the focus in front of the retina, making the yellow fall exactly on the retina. Okay, so that's the duochrome bichrome test. All right, so now we have to check for the near vision, right? And get the if patient is at presbyopic age, you have to get the bifocal correction. So with full refractive correction for FAR, meaning to say your subjective refraction or your net retinoscopy finding or your JCC findings uh, should be placed in front of the patient's eye and then check for the near vision. So there are several tests to do that. The near point of accommodation, the accommodative rule, and the use of plus and minus sphere at a fixed distance. These are actually discussed in a different lectures. Okay, now the easiest way to give the bifocal correction for presbyopics is by determining the age of the patient, and there is an estimated reading add or reading adds for every range of age. So for example, at between 40 to 45, patient can see better at near with plus 0.75 to plus 1, while at the age of 66 to 70 years old, the range of reading adds is plus 250 to plus 275. Okay, so these are the types of bifocals that you can prescribe for presbyopic patients. The one on your left with uh, line and curve shape is the flat top. The middle portion is the executive, dividing the lens into upper and lower portion. The upper being used for distance, the lower for reading, and you have the round segment, or sometimes they call it a scriptop. While on your right is the progressive lens. In progressive lens, you don't see any line to delineate the distance and near vision. And this progressive lens is being utilized for distance, for intermediate, and for near vision. Okay, so here's the way to write the prescription of eyeglasses. So name, of course, and the age of the patient. You write for OD, the power, if you have a spherocylindrical component, the axis, don't forget, and note the vision with that refraction, and the OS for the left, same, the spherocylindrical component, the axis, and the vision with that refraction. And below that, if your patient is presbyopic, you write the add power. By the way, the lowest add available in the market is +1 and the highest is +3. Okay, so, and then after that, you write the pupillary distance. The higher per distance, the lower per near pupillary distance. And write the type of lens and any special order or modification for the lens, such as tint or some other features for the lens. Okay, so take home refraction tips. Number one, always put the accommodation in a relaxed state. When you are giving the final amount of lens, always consider giving the maximum plus but the minimum minus. Okay, so after your refraction, make sure before prescribing, you put your lenses, your final prescription lenses in a trial frame, then ask the patient to walk wearing it for a few minutes. Okay, so at least you would know if the patient is dizzy, which is a sign, dizzy with your prescription, which is a sign of maybe overcorrection, or the patient cannot tolerate your prescription or cannot tolerate the presence of astigmatism. And also take into account vertex distance. What is that? The vertex distance is the distance between the tip of your cornea and the back surface of your lens. So changing the distance of the lens, making it, placing it farther or moving it closer changes actually the effective power of the lens, especially for high prescription lenses. Okay, so that's all. Thank you very much for listening.